Okay, so welcome back to 7.2.2. This is gravitational field strength. So let's recall from last lesson where we defined gravitational field strength. We defined it as the force per unit mass in a gravitational field. Now, up to this point when you were learning about gravitational field strength, you've typically taken it as a constant. So you'll be familiar with G equals to 9.81 newtons per kilogram or meters per second squared. That's actually the value of G on Earth, on the surface of the Earth. But from now on, the value of G will change depending on where you are, what planet you're near, what star you're near, etc. So the gravitational field strength depends on two things. It depends on what the mass is of the body that's creating that gravitational field. And it also depends on the separation from the test mass, which is what we're testing to see what gravitational field strength is at that point, and how far that is from the center of mass of the body creating it. So here's a body called M1. That's the planet or star that's creating this gravitational field. And we have a smaller mass, M2. This smaller mass is going to be our test mass. The separation between these two, again, we label that as R. And then we're going to use two equations. We use F equals mg, which is what you guys have done at AS already. And in this case, M is going to be M2, so it's the force experienced by M2. The little mass. So you can imagine this as the force that you experience on the Earth, or the force that you would experience if you were to go up into space, but you're still near the Earth. So you'll still have a gravitational field over there. You'll still be attracted by the Earth, or to the Earth. And also we recall the equation from last lesson, which is Newton's law of gravitation. F equals to G m1 m2 all over r squared. Now what we're going to do is we're going to equate these equations together, because both of these equations describe a force that is experienced by the mass m2. So when we equate these two equations together, we get m2g equals to big G m1 m2 all over r squared. And then you can see m2 is on both sides of that equation. So m2 is cancelled out. So now you can see that G only depends on the big mass that's creating the field. It does not depend on the test mass that you put into that field. So if we're describing the Earth's gravitational field, it doesn't depend on your mass, it doesn't depend on my mass. We're only talking about the Earth's mass. So we get a nice equation out of that, which is that G equals to G m over r squared. Put a box around that, that's an equation you need to know. We can do a quick test of this to see if it works by putting in the values for Earth. So for Earth, the mass of the Earth is equal to 6 times 10 to the 24 kilograms. And the radius of the Earth is equal to 6,400 kilometers. So if you were to put these values in, you should get a value about 9.81. So we can use this to work out the value of G anywhere. So let's do an example. we have a satellite which is 2,000 kilometers above the Earth's surface. So what I want you to do is A, what is the value of G? And B, what is the force on the satellite? So I'm going to need to give you a few more values here before you can solve that. So I'll just list them all here. The mass of the Earth, 6 times 10 to the 24 kilograms. The mass of the satellite is equal to 1.2 times 10 to the 3 kilograms. And the radius of the Earth is equal to 6,400 kilometers. So you can pause the video here and see if you can solve these questions, and then unpause the video when you're ready to see the answers. So, to solve this problem, we're first going to write down the equation that we need, which is that G equals to Gm over R squared. Now, in the question, we've been given how far the satellite is away from the surface of the Earth, but we take the separation to be from the center of mass. So we actually have to find the separation by doing the radius of the Earth plus the height above the surface of the Earth for the satellite. So, R is equal to 6,400 times 10 to the 3 plus, if we go back, it's 2,000 kilometers above, plus 2,000 times 10 to the 3. That gives us a value of R equals to 8,400 times 10 to the 3 meters. Now we put our values in to the equation. So G equals to, we put the value of big G, which is the universal gravitational constant, 6.67 times 10 to the minus 11, times by the mass of the Earth, which is 6 times 10 to the 24, divided by the separation, but we have to remember to square it. So it's 8,400 times 10 to the 3 squared. At this point you type this into your calculator, and then we get a value of about 5.7 newtons per kilogram. Finally, we do a quick sanity check and we say, how do we make sure that we've done this correctly? Well, we think if you're far away from the Earth, should gravity be getting stronger or weaker? So as with any field, if you're far away from the charge that's creating it, the force or the gravitational field, for that matter, should be getting weaker. So on the surface, it's 9.81. This far away, it's 5.7. So it has, in fact, gotten weaker. So that seems like a correct answer. Then, for part B, we have to use F equals to Gmm over R squared to work it out. M1, M2, all over R squared. But notice how in finding G, we've already done Gm over R squared. So if we've already done Gm over R squared, this Gm1 over R squared, we can just substitute that for G. And you'll notice it gives us a familiar equation, F equals to M2 g, where m2 is the mass of the satellite. So now we simply sub our values in. So I'm going to reuse g from the previous question. So F is equal to 1.2 times 10 to the power of 3 times by 5.7. That should give me a value of about 6.8 times 10 to the 3 newtons. Always remember to include your units. Now, we turn to a new page in our notes. In the previous question, I did F equals to m2g.
Yeah, that line, the first line.
Yeah?
The first line of the slide.
This.
No, the first line. Oh, up. Yeah, you did F equals m2g. So why did you do that, not F equals m1g?
Because m1 is creating that field. So we're looking at the force experienced by m2. So what force is experienced by m2? It's m2g is experienced by m2. m1 is creating that force, that field in the first place. So we can look at it here, for example. It's actually happening in this same question. So you got g equals to gm over r squared, or gm1 m2 over r squared, right? So look at the second one. F equals to g m1 m2 over r squared. m1 and m2, we can choose what we want it to be. I'm choosing m1 to be the big one and m2 to be the small one. And then, so if we look at F equals to g m1 m2 over r squared, if we look at the previous question, we've got g equals to gm over r squared. So we're looking at the field strength that's created by that planet, so by the Earth at that point. So at r squared, if we use the planet, then that m in gm over r squared is m1. So think of that as gm1 over r squared. If I've worked out gm1 over r squared, and you can see here, this equation is gm1 m2 over r squared. This is already gm1 over r squared times by m2. gm1 over r squared was little g. So it's m2 little g. So it goes around in a circle and comes back to the same equations again that you're familiar with. Is that right? All right. So let's write down a title inverse square law. Now the inverse square law is just a mathematical description of anything which changes as 1 over r squared. So the simple explanation is, if something is proportional to 1 over r squared, if you double the distance, you're going to quarter the force, or the field strength. If you triple the distance, you're going to do 1 over 9, the force or the field strength. If you quadruple the distance, you're going to 1/16 the force or the field strength. Let's look at how that works. So here we have a planet again with mass m. It has a radius of r. And then we sort of do like a line. And we've got values here, which is 2r, 3r, 4r. Now, 1 over r squared appears in both the equations for f and g. So that means that both f and g obey the inverse square law. So let's do let's do a few tests of this equation at different values of separation. So we say that G equals to Gm over R squared. At R, capital R, which we defined as the radius of this planet, then G equals to Gm over R squared. So we're going to define this value of G, the original value of G, as the value of G at the surface of this planet. Then we're going to test it at different values. So, at R, at 2R, at 3R, and at 4R. And then we'll put G here. So we've already defined the very first one. At R, G is just G. At 2R, we put 2R all squared. So not only is the R squared, but the 2R is also squared. So when you put it into there, I'll just make a quick note here that I'll rub off afterwards. If we put 2R into there, we get G, the new value of G, equals to Gm over 2R all squared. That's equal to Gm over 4R squared, which is equal to 1/4 of the original Gm over R squared. And the original Gm over R squared, this was just equal to G, because we defined that value of G to be at the surface. So when we're at 2R, oops, should be a G. When we're at 2R, the value for G actually becomes 1/4 G. So here we've got 1/4 G. And if we did that at 3R, we'll get 1/9 G. And at 4R, we get 1/16 G. So that's the inverse square law. We can visualize this as a field lines. Now on the surface of the Earth, if you were to just draw a flat surface and you drew the gravitational field lines, you simply draw parallel lines that are equidistant from each other. But if you looked at it to the point where the Earth was a sphere, or any planet was a sphere, or any object creating a gravitational field was either a sphere or a point, then we call its field lines radial, because they move outwards as if they were a radius of a circle. And then you'll see that the density of these field lines, how close they're together, they get further apart the more you move. So let's draw one of these field lines. So here we have some mass. We're going to draw the gravitational field lines. Then they would look like this, with the arrows pointing inwards. The arrows tell you what direction a force will be experienced if you were to place a test mass in that field. So you can see if you were to put your finger on one of those field lines near the mass, then the next line will be fairly close to your finger. If you were to place your finger on the line that's quite further out, so when you go far away from the mass, then you'll notice that the distance between your finger and the next line actually gets bigger the more you move out. So the density of these field lines is a representation of how strong that field is at that point. So the closer you are to that mass, the closer these field lines are, the stronger the force is when you're near it. When you're far away, the field lines get weaker. Or they get further apart, so the field is weaker. And that is the end of 7.2.2.